Okay, so slope formula is right here for us. It is our average rate of change. You'll notice in parentheses right here that he has AROC. Sometimes I may shorten that to AROC. We really should say average rate of change like on the AP exam. I haven't talked too much about the AP exam, but I'll talk about it a lot. There is a multiple choice section and there is a free response section. On the multiple choice section, it's like any test you've ever taken on the computer. You just read the question, choose the correct answer, right? But on the free response section, you have to show your work. Last year was the first year they did this. Before it was all on paper, but it's on the computer. You read the question on the computer, and then you have a booklet that you write your answers down. And it's basically just blank space. It'll have like a box for 1A and 1B. And so your test will have four free response questions. Each one of these free response questions, give you an idea of what we're working with here. You get 15 minutes per free response question. They have parts. They're long questions where you got to work things out and show your work and explain yourself. So if you're asked to find average rate of change, or you need to reference the average rate of change, please write out average rate of change. If you shortcut it on your homework, I don't care. Just make sure you know what it stands for, because we don't want to do that on the AP exam where it counts big time. They're probably going to take it because it's a pretty common abbreviation, but we don't want to risk points for little things like that. Take another couple seconds and write that all the way out. So average rate of change is just slope formula. It is y2 minus y1 over x2 minus x1. Change in y over change in x. So if we are finding the average rate of change for a function, this is something I don't think you've done before because you've only really done average rate of change for lines or points where you were dealing with something that had a constant rate of change. What you're going to do is you need to find the value of the function for the given intervals, and then find the slope between these 2 points. Especially at first, kids really have a hard time picturing what's going on here, because usually you've had a line and they're find the slope of this line, right? So if we're looking at average rate of change on this interval, we're talking about looking at a line between the endpoints. This first question is not a calculator active question, but I am going to pull up Desmos just for us to graph it and think about what we're talking about here. So if I have f of x equals negative x to the third plus 3x, and then I am thinking about here between negative 2, which is right here, and negative 1, which is right here. It looks like this point is at negative 2, 4. No, 2. Zoomed in. Negative 2, 2, and negative 1, negative 2, I think. So we're looking at these 2 points right here. So what we're thinking about doing is thinking about the slope between that line. One thing I like to sort of give you an example of, if you drive from here to Winston, and let's say that it is 50 miles to get from here to Winston, and it takes you 1 hour to drive there. What is your average speed on the way to Winston there if it takes you 1 hour to go the 50 miles to Winston? 50 miles an hour, right? So your average speed is 50 miles an hour. Now, those of you who have driven from Elkin High School to Winston, were you probably going 50 miles an hour the whole time? No, you should be going 25 on Elks First Street out here. It's hard. It's very hard. That is a very low speed limit. But you should be going 25 out here. You should be going, 35, 40 through town. But when you get on 77, you're going a lot faster, right? 421, a lot faster. So what we're looking at when we're looking at average rates of change is this, like this line, this is not a line right here between this point and this point, right? It's a curve, right? But we're looking at, if we put a line through the endpoints, what would be the slope of that line, right? So, so just because we're finding an average rate of change does not mean it's linear, right? And in these cases, it's not linear at all. So whenever we're doing this, though, it's pretty straightforward what you're going to do. We are going to just plug in -2 and -1. And another thing that's different in AP Precal, our test has large calculator inactive sections on it. Multiple choice, I think you've got 40 multiple choice questions. Only 12 of them are calculator active. On the free response, you've got 4 free response questions. 2 of them are calculator inactive. So you got big parts of the test that you can't use the calculator on. So they're not going to give you anything outrageous that you have to do by hand, but they'll give you something like this that you have to do by hand. So this is a shift from Math 3, because in Math 3, you can use Desmos on everything. So in general, when we teach it, we don't really restrict your use of Desmos too much, or at least I don't at all in regular Math 3. There might have been a few things Miss Martin was like, no, can't use Desmos yet on that, but we will have to do a lot of this stuff by hand. So make sure, like on your homework, do it by hand. Don't type it into Desmos because you need the extra practice for it. So we've got f of -2, and also, we want to practice good notation here because, like, real people are going to be grading your test. I grade AP Calculus tests, or I have for the last couple of years. I have not done pre-cal because they're graded at the same time, and you can't do both. But, you know, they hire, like, actual teachers to, like, follow the rubric and grade these tests. So they're looking for specific things. So your work needs to be well organized. It cannot be just chaos thrown on the paper. So whenever you plug a number in, label it that you're plugging the number in. So label it by doing f of -2. And then we're going to have -2 cubed plus 3 times -2. This will be a little bit of a practice in your order of operations here. What have we got to do first? Exponents are going to come first, so we'll get, this negative right here stays. -2 to the third power is -2 times -2 times -2, which is going to give us -8. And then we'll get positive 3 times -2 will give me -6 here. But where I've got the negative right here, -8, that actually becomes like a positive 8. So 8 minus 6 is 2. So what that just gave us, the x coordinate that we plugged in was -2. The y coordinate that we got out was 2. So that's our first point that we have. And then we're going to do the same thing for the -1. So we'll have f of -1, and we'll have -1 cubed plus 3 times -1. And that's going to give us -1 minus 3. And just like the last piece, that negative becomes positive. This time we'll get -2. So our other point is -1, -2. And then, once you get that, you're going to do your slope formula, which is y2 minus y1 over x2 minus x1. So, you know, you could let this be x1, y1, this one be x2, y2, or you can switch it. It doesn't matter which point is x1, y1, and which one's x2, y2. So your work could look a little bit different than what I'm doing here, and you could still get the right answer, but I would have -2 minus 2 over -1 minus -2. That double negative right there becomes a positive. We're going to get -4 over 1. So we just get -4 for our final answer there. Okay? Try that second one on your own. Okay, so your interval that you're looking at here is 1 to 4, and you're going to do basically the same thing, but with a different equation there. I'm going to freeze my screen so I can work it out. You're going to get a little work with some fractions here. Excuse me. This one gives you lots of good practice those fractions. See how rusty we are. Math 3 will really ruin you by relying on this math for anything you find slightly. Yeah, don't leave me, or not your problem, but a complex fraction. Like, don't leave me a fraction inside of a fraction. So like if you've got a fraction over another number, go try to get it all the way simplified down. That. Which ones go together? Is it 3 over 3 divided by 14, or is it 3 divided by 3? I need it not to be fractions inside of fractions. So keep going. How do we divide fractions? It's one of my favorite sayings. I love to say it. I don't know if your other math teachers love it as much as me. You guys have had me. I've got a couple of my former students. Dividing fractions is easy as pie. Flip the second and multiply. Also, I'm going to pick on Evan a little bit here too. Evan is doing the slashy fractions here, like this. They can cause some problems in this class, particularly with complex fractions, because when we got like something like this, it starts to look really confusing. So I think the slashy fractions look prettier, and through most of my high school math career, I went slashy fractions, but I eventually decided I was going to have to switch. So I suggest writing your fractions like 1 over 2, like that. if you do use slashy fractions, you need parentheses. Well, it's not a bad idea to use some parentheses anyway. But especially whenever using the slashes, you're definitely going to need some parentheses if you're doing anything besides just that. Also, like, if I have like 3 1/2, I know that's 3 1/2. If I write, I don't know if that's 3 1/2 or if it's 31/2. So slashy fractions will give you a little bit of trouble. And as much as I hated doing it, I would suggest changing your ways at this level. Keep your time, but you got to keep going because you don't really fractions inside fractions. Yeah, you're close. Like I would do some fraction and then 5 fractions. You're close. You're close. Where are you at? Okay, common denominators. Got to get common denominators. Doing pretty good. Yeah. Well, I was going to say, she doesn't come in this period. I don't even know she drives. Sarah said she could come in the last 30 minutes of one period.
Okay,
If that'll work.
yeah, it's fine. I was going to mention something. With the alternates made the rest of the week.
Right.
So what do you do?
Right now, not much
Okay.
because we just got started. So if
Y'all
you
go to the meeting center. That's where there's like 40 kids going to be at the meeting center. I'm going to tell the whole.
Yeah. Okay. Yeah. We can do that. Yeah, because I'm gonna have those at the end of the year.
That work?
Also, we probably need to check too. She's got that CNA class in the mornings.
So
I don't know what that means for. Is it okay if we do it afternoon?
That's not a problem.
Yeah. Because I know that they're not allowed to miss much of that class.
That's fine.
Yeah.
That's
Okay.
fine.
All right. Okay. All right. We've spent longer on this problem than we probably should, but a little fraction struggle is a good thing for us here because you got to be able to do it. And what we're going to see, like rational functions are in this class too. Like we're going to have to do some of this stuff with variables eventually, so we definitely have to be able to do it with numbers. You should get 1/14. So let me zoom in a little bit here and walk you through it. I think I saw a lot of people getting close. I only saw a couple of you getting to 1/14. So most people, I believe, were getting the points fine, right? You just plug in 1, you get the point 1/2, and then you plug in 4, and you get 4 1/2. I saw most everybody looked like they were doing pretty good with that. And then you're going to plug that into slope formula. Again, not really much of an issue there, but this is when you actually have to start doing some work with fractions, right? So from here, we've got 1/2 minus 2/7 over 4 minus 1, or you may possibly have 2/7 minus 1/2 over 1 minus 4. That would also work. The first thing you want to work with is you're trying to get this top stuff put together, right? So to add or subtract fractions, you have to have common denominators. We got 1/2 of a pizza and we got 2/7 of a pizza, right? This pizza is only cut into 2 pieces. We got 1 out of the 2 pieces. This pizza is cut into 7 pieces. We got 2 of the 7 pieces. We can't just slap those together because they're not the same size pieces, right? So we got to get common denominators 14 is going to be your common denominator here. So to do that, we just multiply this fraction by 7 on the top and bottom. That gives us 7 over 14. We multiply this fraction by 2 on top and bottom, which gives us 4 over 14 right here. All right. Now we got the same size pieces of pizza. We got 7 pieces minus 4 pieces, which gives us 3 pieces. The bottom stays the same because that just tells you what size pieces you're dealing with. Right? So, and then obviously here we just do 4 minus 1 gives you 3. So we got 3 over 14, and I would keep some parentheses here, over 3, but notice what I did here. I went ahead and put that 3 over 1, because I am dividing fractions here, and I would really rather them both be fractions. So if you have a whole number, and it would be easier for it to be a fraction for you, just put it over 1. It's the same. We're good here? Okay, then my favorite phrase, dividing fractions, easy as pie. Flip the second and multiply. So 3 over 14 times 1 over 3 right here. I just went ahead and canceled these 3's. I reduced before I multiplied. And so that gives you 1 over 14. You can also get 3 over 42, but if you do that, then you need to reduce. And 3 over 42 is not a very obvious reducible fraction, right? So if you reduce before you multiply, then you'll be a little bit better off. Yes?
Does it change if you like the other fraction?
Yes, it'll be wrong. The one on top is your first fraction. The one on bottom is your second fraction. Yeah. So whatever is on top is your first fraction. And if you keep parentheses, that helps you too. Because like, you know, if you've just got 3 over 14 over 3, it's kind of hard to know whether it's this or whether it's this, right? So if you keep the fractions at like parentheses as you're working, that might help you keep it straight a little bit.
Yeah, I think
Yeah, there is. Because division is not commutative. Like if I have 20 divided by 5, I will get 4. 5 divided by 20 is not 4, right? Whereas like multiplication, it doesn't matter the order that you do it in, or addition. So if it was a multiplication or addition, it wouldn't matter. But for subtraction and division, we can't switch those two. Top fraction is your first fraction. Bottom fraction is the second one. That's the one that gets flipped. Okay? All right. I love this problem. It's like a crash course in almost everything fractions right here. But we've got 1/14 as our answer. All right. You won't have to do fractions all the time like that, but we got to be ready for them whenever they come along. Right? You know what? Did I? No, I think we're okay on this. I don't think I changed these. Moving on. You will be asked to do some of these from a graph instead of from an equation. Really, I think they're even easier because it's asking us for the average rate of change of G on the interval from -1 to 3. So when we're looking at -1 to 3, -1 is right here, 3 is right here, so we're looking at this point, and if we go up right here, we're looking at this point. So you have 2 options for this. You can just give me the coordinates of those points. So we got -1, 0, that's the coordinates of this point. And then we've got 3, 4. That's the coordinates of that other point. We'll do slope formula with those. So 4 minus 0 over 3 minus -1. That's a double negative, so it's really like adding. We're going to get 4 over 4, which is 1. Another option on these, instead of using the points, I could just draw the line in right here and count the slope. So like, if I look at this, I'm going up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. So the slope is 1 for that. So you wouldn't necessarily have to show work if you did it that way. Okay, questions? All right, multiple representations. I told you yesterday it's really important. We have to know how to look at these several different ways. So this one's a table. It's also in context of a situation, like a real world situation. So the table above lists the life expectancy of U.S. females born in a given year. Find the average rate of change in the life expectancy of U.S. females born from 1850 to 2000. Include the units of measure. This right here is going to be important right here. Include units of measure, right? Don't forget to do that on any problem that has units involved. It would be like if I ask you how tall you are, and I ask Braden how tall he is, and he tells me 74. That would seem weird, right? He probably would mean 74 inches tall, but nobody answers with 74 inches whenever you say that, right? We have like assumptions that we make. So you want to say your units so that we know specifically what you're talking about. We are looking from 1850 to 2000. So 1850, 2000. We really don't need the in-between stuff, right? We just need those two endpoints because we're talking about average rate of change. So we are going to use the point 1850, 46.1, and 2000, 81.83. So we will have 81.83 minus 46.1 over 2000 minus 1850. I don't know if they're going to give this to you without a calculator or not. I feel like they probably wouldn't. So I'll just give you the answer here. So we got 81.83 minus 46.1 is going to give you 35.73. And then on the bottom we'll get 150. Okay. And then you can divide those two, and you're going to, oh yeah, I'm pretty sure they're not going to make you do this without a calculator because you're going to get 0.2382. But we've got to include units of measure. So what I like to do is I just like to look, okay, these were my y coordinates right here on the top. The y coordinates, right there's the units for the y coordinate, right? So the top is in years. Let me double-click in that table. This is in years. And the bottom is in, oh, let's see. This is age. This is a weird one. It's age in years. And then 150 is also years. This is weird, right? But so our answer is 0.2382 years per year.
It's like an increase in life expectancy of 0.2382, right?
Yeah. So say it in a sentence for me using the units.
The sentence I found is there is a 0.2382 increase in life expectancy each year.
Correct. Right. So there is a 0.02382 year increase in life expectancy every year. Right. So when I just write years per year, that seems crazy, right? But what we're talking about is life expectancy is increasing like about a quarter of a year every year that goes by. There. So it's a little confusing to look at, but if we really walk through it, we can kind of see what it means there. All right. All right. Now, we, oh, I did change this because yours does not say 0.99 right here, does it? Or I hope not. I meant to change it. It doesn't. It's got, has it got 1 point? Yeah. Okay, that's what I want it to be. Now, the idea of instantaneous rate of change. So, like what we're talking about is not instantaneous rate of change. It is on average what is happening. It is if we drive from here to Winston, our average speed is 50 miles an hour, right? It does not mean we were going 50 miles an hour much at all necessarily, but it's our average speed. We also sometimes are interested in instantaneous rate of change. Instantaneous rate of change is whenever you're driving from here to Winston and the cop is on the side of 421 and they take out their radar gun and you're going 85 miles an hour. That's your instantaneous rate of change. Does the cop care that your average rate of change from Elkin to Winston was only 50? Are you going to talk him into that? But sir, I drove slow here so I can drive faster here. Is that going to work? No, it is not, right? So instantaneous rate of change, you can think of like your radar gun speed, right? Average rate of change is for the whole trip overall. So instantaneous rate of change is a calculus idea. We're not going to get into it deeply, but we're going to talk about approximating average rate of change. So instantaneous rate of change can be approximated using the average rate of change over smaller intervals. So, let's see. I'm skipping ahead to see how much more I've not got anything else that's calculator active. So we're going to do this one. I'm going to do this one for you. I don't want to drag out the computers for this one problem right here. But I'm going to show you a couple of cool things about Desmos that you may already know, but you may not. So we got a ball thrown vertically into the air. Its height is going to be given by this equation right here, right? If we type this into Desmos, you can use h of t. It will let you use t. I find it easier to switch it to x because there are a few limitations of things it will do if you use t. So mostly in calculus, not as much here, but I'm going to switch it to an x because it grasps it. It does it a little bit better. So we're looking at, here's our height of our projectile that's thrown, our ball that's thrown. So if I look at 1, right? So if I plug in 1, here's the cool thing about, like, I could do negative 4.9 times 1 squared plus 25 times 1 plus 5, right? And I'm going to get 25.1. But you also can just do h of 1, right? So Desmos plugs it in for you if you do it that way. So if I do h of 1, it gives me 25.1. So I know that I've got the point 125.1. And then I've got I need to do h of 1.1. So that gives me 26.571. So I got the point 1.1, 26.571. And then I need to do slope formula with that, right? So if I do slope formula, I would have 26.571 minus 25.1 over 1.1 minus 1. And that gives me 14.71. So I could also graph like this is the point we're talking about right here, and then we got 1.1 h of 1.1 right here. And we're talking about like the little line between there that is has a slope of 14.71, right? So now that already looks pretty linear, right? If we just look between that little piece right there, it's not a straight line, but it looks awfully close to being a straight line right there, right? Now, what I can do is I can go over here, and I can now, well, instead of using 1.1, what if I do 1.01, right? So now instead of looking at this point right here, I'm going to change this to 1.01. We're talking, oh, even closer. Let's zoom in a little bit more. Now that, I mean, it already looked pretty much like a straight line, but this looks really a lot like a straight line, right? So if I do 1.01, I'm going to write down that 1.01, the y coordinate there is 25.25151. I think that was right. And then I'm not going to write down the other point because it's just like we're using the same point, 25.1 for all of these, right? So if I take this number right here and change it to 25.25151, I think I wrote that down wrong when I wrote it down, and change this to 1.01, now I've got 15.151. So now I've got 15.151. Alright, then I could keep doing this. I'm just going to do it on Desmos for you instead of writing a lot of stuff down here because we need to move on to the next stuff. So I'm going to put another 0 right there, another 0 right here, another 0 right here. Now I've got this number right here. So now I got 15.1951. 15.1951. And then the last one there has us add one more 0. And this number right here. And so now I got 15.19951. Okay. So what we see is like the closer we get to the actual point, the closer we're getting to the actual exact slope at that line, right? So we can estimate that instantaneous rate of change. What do you guys think it's going to be? 15.2 would be my guess. That would be my guess on what we've got here. Now, I also know that in calculus, this would be h prime of 1 that you don't know anything about yet, and it is, in fact, exactly 15.2. So we would have a really good guess there if we did that. There. So the rate of change there is 15.2 at that point. So by getting closer and closer and closer, we can get closer and closer and closer to the exact slope of that line at that point there. So that is our way to estimate instantaneous rate of change. We won't be asked to find the exact instantaneous rate of change anytime because that's calculus. But we might be able to estimate it, and if we're estimating, we're just going to use like really close to that point values. All right, so to sort of summarize right there, we cannot find the rate of change at a particular point in AP pre-calculus. That is a calculus problem. But we can estimate, the rate of change at any point by finding the average rate of change over a very small interval. We can estimate rates of change at two different points by estimating individual rates of change using the concept of a tangent line. So tangent lines, I gave you like a little bit of a sneak preview on yesterday there, and we talked about those. So this goes on here to talk about if the graph of f has a positive rate of change, then the graph of f is increasing. Right? This is that chart that we had on the notes. In fact, did I put it in here later? it's basically this right here. Do you guys have that? Or did I change that? I may have changed this. I think I've opened the wrong thing. I think I took this off and replaced it. Let me open up. I think I condensed. Oh, I did. I should have opened this one. This chart, it's this one right here, was on yesterday's notes. We filled it in right. If the rate of change is positive, the graph of F is increasing. So let's talk about just a couple of scenarios, and then we're going to probably have to go on. For each scenario, we're supposed to determine whether there's going to be a positive rate of change or a negative rate of change. So we're thinking, as independent variable increases, what happens to the dependent variable? Is it going down or is it going up? So a child's age versus the child's height. So as age increases, what's going to happen to height, or should happen to height? Increase, right? So this would be a positive rate of change. Sorry, right there. Okay? All right. Golfer's skill level. So as the golfer gets better and better and better, what should happen to the golfer's score? Should go down, right? Because golf is a backward sport where low scores are good. So this is going to be what type of rate of change, Zane? We're talking about just positive or negative here. So our graph will be decreasing, which will give us a negative rate of change. Okay? The height from the ground of a coin dropped off the Burj Khalifa, which is your tallest building in the world, versus the speed of the coin as it falls. I think this one's hard. So, the height from the ground of the coin drop. Sometimes I have to so that is height. And then speed. All right, so if our x-axis is height, right? This graph you would, if you're thinking of observing it, you would graph it backward. You're going to graph over here on the right side because you're dropping the coin from the top, right? So we're talking about height is really high over here, but what is happening with your speed? Right before you drop it, that coin has 0 speed, right? So we're very high, but also stationary right here before we drop it. Then when we drop it, the height is going to decrease. What's going to happen to the speed? Increase. So the height will decrease, the speed will increase. Height will decrease some more, speed will increase. In fact, well, I think speed is linear actually. Distance would be quadratic, but this would be linear until it were to hit terminal velocity if it does. So in this case, you kind of have to graph it backwards, right? For what's happening here. What type of rate of change do we have on that graph? As the height increases, speed's actually decreasing, right? It's hard to think of this one because it's the opposite of what's happening when you watch the coin fall. If we had time on that x-axis, speed would be increasing, right? It goes faster and faster and faster as it falls. But we don't have time on the x-axis. We have height on the x-axis. So this is a negative rate of change. And unfortunately, once again, I tell you, I'm always, and the bell's going to ring here.